them up here pretty quickly so you can check your work. Whichever ones you did, great, you can check. Whichever ones you didn't do, you should do. Notice this is a homework assignment. On the quiz day, I will most likely also do a homework collection. So I'll probably grab some worksheets, a lot of worksheets in this unit for graphing. So don't like throw these away, hang on to them. If we do parts in class, that's awesome. That's just a benefit for you. But ultimately, I'll be wanting to see that you've completed these assignments. Okay, +2 out on the end moves every point up 2, technically called a vertical shift. I don't care if you know it's called a vertical shift. If you just know number out at the end is up and down, that's cool. Just like it was for log graphs, just like it was for exponential graphs, just like it is for any function graphing. Like a parabola, you may have done this with in Algebra 2 is what I'm hearing. Any function that you're graphing that had a basic form, +2 at the end, moves the whole thing up 2. So I would most likely move my baseline up. So remember the x-axis, I like to call that the baseline for the sine curve and the cosine curve because it's sort of where it's like home base for the curve. So if I move the baseline up 2 and I build my curve around that new baseline, and I can go kind of backwards too and get the backwards part, that'll work. Alternately, you can draw an original sign. So you can kind of go down here and go, okay, I'm going to make a sign. Sign, 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 sign. There's my sign. And then everybody moved up 2. And we got our new graph. Every single sine and cosine graph has the same domain. Nobody misses that question. That's how I know you totally don't listen. Because if you miss that question, you are absolutely not listening to anything I'm saying. Because that's the easiest question, because it's always that answer. Every sine and cosine. Range in this case, well, normally -1 to 1. But if we go up 2, the lowest number now is a y of 1, and the highest number is a y of 3. So -1 plus 2, 1 plus 2. Okay. Similar thing on this guy. Not going to do as much talking on him. Here's where he should look like. Right. Yeah, we're supposed to make them round. Do your best to make them round and not pointy. They're not pointy. That's the baseline. -infinity to infinity. -3 to -1. Whoops, that doesn't look like a -1. That looks like a -7. Okay. So, down 2. All right, up and down, yep. 3 out front, that's a stretch or an amplitude change. Now, amplitude is the distance the high and low points are from the baseline. All right. Amplitude is maximum distance from the baseline. In a normal sine curve, my amplitude is 1. In 3 sine, hi, come on in. No worries. Thanks. And neither one of them are here, so we'll see. Okay, so if I take a normal sine curve and I stretch, the thing about stretching, the baseline points are locked in. They don't get stretched. This stretches from 1 times 3 up to 3. This stretches from -1 times 3 down to -3. So 3 times the normal amplitude. So there's that guy. He's the normal one. I meant to do him a different color, which I can't do because I can't hit that. So that's the original, and that's 3 sine. Sine is considered what's called an odd function. That means it, from the origin, it has rotational symmetry, which means it goes from here, it doesn't go back up, it comes down. So from the origin, it kind of does the opposite thing. Sines go woo, like that from the origin. So that's what that would look like on both sides. Domain, we don't miss the domain. Range, -3 to 3. All right. So number out in front is an amplitude change or a vertical amplitude change or a vertical stretch. Problem number 4, hopefully you didn't miss that. That negative out in front is where we're going to take this and reflect it. We're going to reflect it over the x-axis. And a lot of times what we, at least at Westfield, seem to like to call that is we call it a direction change, because if you kind of think about the sine curve, when it starts, it goes in a certain direction. When we do go in the opposite direction, instead of going up, we go down first. Amplitude of 3/2 or 1.5 or 1.5. We're just gonna have to kind of eyeball that. So here's what that side would look like. And then this side. So we get a down and then an up this time, and then on this side we do an up and then a down. We don't miss the domain. Range, -3/2 or -1.5 to +3/2 or +1.5. Yes, sir.
Since it's -3/2, wouldn't that be -3/2 plus 1 plus -1, if that makes sense?
So it would be -1 okay, hang on. Wait a minute. Oh, it's vertical. Okay, so vertical shifts get added on. Vertical stretches get multiplied. So the way the range turned into this, if you want to think, okay, it's originally -1 to 1. It's like it's -1 times 3/2 and 1 times 3/2. Does that make sense?
Yeah.
Okay. Go ahead, Chloe.
So if it's reflected, it's pretty much just going like the opposite way.
Yes. That's one way, especially on something like a sine curve that like when we're drawing it, it's almost like it's moving. It's like, woo, woo. It's got movement to it. So a normal movement of a sine curve from the origin is you start off going uphill. A negative means you go downhill first. You go in the opposite direction. It's going to be harder. That's even a little trickier for a cosine. We'll do that in a minute. Technically, the official mathematical way to describe what we just did is we're reflecting it over the x-axis. So what's normally there, whatever's the bumps that are up flip down, and the bumps that are down flip up. Okay. When we've got to combine a couple of these, we've discussed kind of different options on how to approach them. I tend to do stuff that's out front first. I know, what do I do? I don't know. I kind of do it both ways. I definitely try to do one thing at a time, okay? So when I look at this and I'm like, okay, I'm going to have to flip it, and I'm going to have to move it up 2. Honestly, I would probably flip it first. I think I actually do what's up in front first. So I imagine, okay, I'm going to flip this thing. I'm going to reflect it. There's the reflection. And then up to new baseline points, but it's the reflected version. Yeah, I think that's a good thing. Reflecting is usually the thing. I was just going to say I do it last, but I don't. I don't know. This is when I struggle, because I'm like, what's my advice to you? I don't know that I have advice. I think you can do it either way, but you do have to be careful about kind of how you think about it with order of operations. So if we're consistent, that's probably going to be the best. If you find a way that's working for you and you're like, I can't really explain it, but I'm doing it right, then keep doing it, even if it doesn't look like you're doing it in the same order as me. When we've got to do both of these things, this is usually the one that students struggle with. I do think an amplitude change first. And then everybody moves down 3. So that's going to be the new baseline. The baseline points are always easy to lock in. And I think that's probably the thing that helps me the most, is those fixed points that sit, if they're fixed points that are going to sit on the baseline. When I think about that just being a new baseline at -3, and so each of those points gets fixed in, then the other points, I can always double check when this purple guy moves down 2 and this purple guy moves down 2, and I finish like that. Oops, that looks horrible because I don't have a good scale on that side. We'll throw that further down there. Okay. I can always sort of look at the end and think, okay, what do I have? I have a graph that has an amplitude of 2, but it's wiggling around a new baseline. The range is going to be challenging on those graphs. Essentially, it's like we take the -1 to 1 range, we multiply them both by 2, and then subtract 3. So my range goes on this time from -5 up to -1. Because if you take -1 times 2 is -2, and then subtract 3. So your bottom point's going to be at -5, and your top y times 2 minus 3 is going to be at -1. Okay. So that was a really thorough review of the transformations. and applying them to the basic sine curve. If you don't have the basic sine curve points, if you can't just throw that on a graph for me, we're going to be stuck. And there's no reason for you not to be able to do that. So you got to memorize that. You got to know that's what sine looks like, and you should know that how it goes in the other direction. If I want you to draw more of it, you should know that this side of it I'm going to go backwards. Oh, I forgot to get that mean. If I go backwards, I get that. So, all right. It keeps on going forever. It has a basic domain of negative infinity to infinity. We don't miss that question. And it's got a range. Okay. Go ahead and find